Hello everyone, welcome to the .NET office. Today we are going to learn a case study on how WhatsApp handles over 100 billion messages per day. Every day, the world sends over 100 billion messages through WhatsApp. To put that into perspective, that's more messages than the number of stars in our galaxy sent daily. And all of this happens in milliseconds, encrypted, reliable, and handled across continents. Today, we're doing the deepest engineering breakdown on YouTube, how WhatsApp's architecture works end-to-end, how it handles real-time messaging, how its end-to-end encryption works at massive scale, and how group messaging, fan-out, and multi-device support are even possible with billions of users. If you're a developer or system architect, this is your masterclass in real-time distributed systems. So, WhatsApp isn't just a chat app, it's actually a global telecommunications system, just disguised as a simple messaging app. From day one, WhatsApp had a few guiding principles. First, it needed to run on low-end phones and weak networks. This was especially important because, WhatsApp's earliest user base was in India, Brazil, Southeast Asia, and Africa. Places where low bandwidth and unstable networks are pretty common. Second, the app had to consume the least battery possible. It must maintain a stable connection without, draining your battery. Third, it had to give a real-time, always-on feel. Even at massive scale, message delivery must feel instant. And finally, it had to be end-to-end encrypted by default. And behind all these goals sits the core secret weapon, Erlang. It's a language built for telecom switches, SMS gateways, and honestly, millions of concurrent connections. This isn't a coincidence. WhatsApp is basically a 21st century SMS network, but encrypted and global. So let's talk technology for a minute. First up, Erlang at its core. Why Erlang? Well, because Erlang gives WhatsApp millions of lightweight processes, crash isolation through supervisors, soft real-time guarantees, and hot code upgrades, all without any downtime. That's actually why telecommunication systems rely on Erlang, and, WhatsApp does too. Next, let's look at the modified XMPP protocol. WhatsApp started out with XMPP, but then they aggressively modified and optimized it. WhatsApp's version uses binary frames instead of XML, smaller headers, minimal metadata, lower handshake overhead, and, much faster reconnections. Persistent TCP connections. So, when WhatsApp connects to the server, it actually maintains an always-on TCP socket. But why does it do that? Well, real-time messaging really needs a few things. No repeated TLS handshakes, no need to re-establish connections, no polling, and, of course, low battery consumption. This one single decision is pretty much the reason why WhatsApp feels so fast. Okay, let's walk through what actually happens the moment you hit send. Step 1. Creation and encryption. Before a message even leaves your device, it's encrypted using the Signal protocol. Not on the server, not in transit, but right there on your device. The servers only see gibberish, honestly. Alright, so step 2 is about sending your message to the WhatsApp Edge server. Your device actually pushes the encrypted payload over the TCP socket to the nearest WhatsApp server. And, WhatsApp uses this region-aware DNS routing to make sure you connect to the closest data center. Okay, moving on to step 3. The message is now queued. The Edge server stores your message in in-memory queues for real-time users. And for those times when the receiver is offline, it uses short-lived storage. Now, step 4 is all about routing. Each user's connection is handled by Erlang processes that are responsible for things like message state, delivery, ACK handling, and even retry logic, just in case something goes wrong. Alright, so step 5 is delivery. If the recipient is online, the message gets delivered instantly. But if they're offline, the message is just stored temporarily until they come back online. Now, moving on to step 6, delivery receipts. You know those ticks? A single tick means the server received your message. Double ticks mean it's delivered to the device. And when those ticks turn blue, it means the message has been opened. All these states are managed using really small metadata packets, while the actual message content stays fully encrypted. Presence is honestly one of the trickiest parts of messaging apps. Presence includes things like whether someone's online if they're typing recording or just their last seen timestamp. WhatsApp handles presence using super tiny metadata packets, usually just a few bytes. Users are split up across different shards, and every status update gets published to the sender's connections group members and even linked devices. And since presence updates are happening all the time, WhatsApp aggressively compresses and batches them to keep things efficient. Okay, here's where things get really interesting. Group chats can have thousands of members. Let's say you send a message to a group with 2,000 people. WhatsApp must encrypt the message separately for each member, send each encrypted payload independently, and deliver them with the same real-time feel. This is known as the fan-out problem. Traditional solutions. Well, some platforms use server-side broadcast, like one message going out to many subscribers. But WhatsApp cannot do this because end-to-end encryption requires per-user encryption keys. You just can't send one encrypted message to everyone, since each user's encryption session is unique. WhatsApp's approach is server-side fan-out. So, WhatsApp chooses to fan out on the server, not on the client. That means the server duplicates the encrypted payload n times, one for each group recipient. Now, how do they do this efficiently? They use in-memory message queues, custom Erlang processes per recipient, user state tracking, batch delivery when possible, and optimized queue persistence for offline users. Even with over 100 billion messages a day, group messages still arrive in less than 1 second. WhatsApp added multi-device support recently, and honestly, it's a huge engineering challenge. Because of end-to-end encryption, WhatsApp cannot simply sync messages via the server in plain text. So, here's how multi-device actually works. Each device gets its own encryption key pair, and every message is encrypted separately for each device. WhatsApp servers never store long-term message history. Linking devices involves securely transferring keys using QR code pairing. Messages are fanned out to each device separately. Now, just think about this for a second. A group chat with 2,000 members, and if each member has 3 linked devices, that's 6,000 fan-out operations per message. WhatsApp handles this effortlessly, thanks to Erlang and horizontal scaling. Another surprise, WhatsApp stores very little. So, messages are not stored long-term, right? As soon as the message is delivered, it's deleted from the servers. But what does WhatsApp actually store, even if it's just for a bit? Well, there's a queue for offline users, media files that are waiting to be downloaded, and, of course, some metadata like the sender, receiver, and timestamp. Now, behind the scenes, WhatsApp uses a mix of memory-optimized queue storage, highly available replicated file systems, and SSD-backed stores for temporary media. And, WhatsApp's whole architecture is intentionally kept minimal. This helps reduce the attack surface and, honestly, improves privacy for everyone. So, how does WhatsApp make everything feel instant, even when the network is super weak? Alright, let's break down the tricks WhatsApp uses. First, there's persistent TCP with minimal packet size. Thanks to WhatsApp's binary protocol, packets are 5 to 20 times smaller, and that means less RAM and CPU usage too. Second, they use aggressive compression, so metadata gets shrunk down to just a few bytes. Third, there's smart reconnection logic. When networks drop out, which, let's admit, happens a lot on mobile, WhatsApp uses incremental backoff, session resumption, and state replaying to keep things running smoothly. And finally, DNS-based global routing helps users connect to the nearest regional data center, which, honestly, keeps latency super low. So, what happens if the user is offline and, the app is actually killed? Well, WhatsApp uses Firebase Cloud Messaging and the Apple Push Notification service. These services basically wake your device when a message arrives. But hey, remember, the message content always stays encrypted. Push servers just carry wake-up notifications, not the actual message content. Once your device wakes up, it reconnects, downloads any queued messages, and then decrypts them locally. WhatsApp uses telecom-grade fault tolerance, making sure your messages get delivered reliably, no matter what. So, let's talk about fault tolerance techniques. With Erlang supervisors, if a process crashes, only that process restarts, not the whole system. In an active-active multi-region setup, data centers across continents operate simultaneously, not just in failover mode. And if a server node dies, well, here's what happens. TCP connections shift, queues migrate, and message delivery just continues. Most users don't even notice anything. Plus, with hot code updates, WhatsApp can deploy new server logic without restarting anything at all. At last, that's how WhatsApp handles 100 billion messages a day. Persistent connections, end-to-end encryption, server-side fan-out, multi-device encryption, Erlang concurrency, and telecom-grade reliability, all wrapped inside a simple green chat app. Comment which system you want next: Instagram, Telegram, Discord, or maybe Facebook Messenger. And yeah, don't forget to share this with your dev team. Thanks for watching. See you in the next deep